I'm going to be talking about some work that you could think of as a small branch of the big program that my friend Nate Osgood overviewed in his talk. That talk covered lots of subjects, whereas I'm going to be focusing on one. So one of the great things about working on applied category theory is that you can take ideas from pure mathematics and bring them over to meet different kinds of applied mathematics, engineering, and science, where they've been developing all sorts of interesting ideas, very sociologically distant from pure mathematics. But often the ideas that they're developing in these different fields actually are very inspiring when viewed from a pure mathematician's mindset. Category theory tends to be thought of as the purest of pure mathematics, but this is sort of cutting through many intermediate layers and going.
Sorry, because issue with my
right. Issue with this mic? Okay. So this will be an example to see how category theory can connect with some very applied ideas. I've been working with Adittya Chaudhuri, who is working on systems biology, a certain approach to studying biological systems and how complex wholes can emerge from simple parts. And I've been working with Nate on this topic that he introduced under the name of systems dynamics, which is sort of a different subject, but they share a common language, which I'll now try to explore with you here. So Nate mentioned three different kinds of diagrams that they use in system dynamics, and I've been thinking about the simplest one. In one example, the simplest one is simply a graph with edges labeled by plus and minus signs. This describes in a very crude qualitative way how different sorts of factors or entities can positively or negatively affect each other. So this little example here is one that might be familiar to students who are trying to do homework, but no more than necessary to achieve their grades. So as their grades increase, that has a negative effect on how much effort they put into it. But effort has a positive effect on the quality of their work, and the quality of their work has a positive effect on their grades. Unfortunately, also, effort has a negative effect on how much sleep they get, and sleep has a positive effect on the quality of their work. So you see two feedback loops here, both of which, unfortunately, in this example are what are called negative feedback loops, meaning that if you go around the loop multiplying the signs, you get a minus sign. For a negative feedback loop, it tends to make things not explode exponentially, but just level off to an equilibrium. So J. Forrester introduced a lot of concepts of systems dynamics in his book Industrial Dynamics in 1961. And if I do it sort of out of order chronologically, John Sterman, another professor at MIT, formalized these three different diagram languages, of which I will only be talking about the causal loop diagrams, in a book called Business Dynamics in 2000. But this tradition, while it has these roots in trying to understand the business cycle and things like that, it's applicable to many other areas. Pinar Senga introduced some of these ideas to as a kind of tool for people advising companies to improve their organizational structure in this book called The Fifth Discipline, which was quite influential. But I find a kind of spin-off of that book much easier to extract mathematics from. This book, by Daniel Kim and Virginia Anderson, called System Archetype Basics in 1998, was really an eye-opener to me, because they introduced some very simple causal loop diagrams, which they call system archetypes, which are basic ways that a system can behave. And then finally, in creating these models, Nate has pointed out that what you want to do is you want to go in and interact with a community of people who are having the problems that are to be modeled, and you need to sometimes show them these diagrams to show them your model and get them to critique it and improve it. And Peter Hovmand formalized this to some extent in a book called Community-Based System Dynamics. And I've realized that category theory is really important, not so much in creating software that can be manipulated by experts, but in creating an environment where non-experts can help build a model out of smaller pieces. That's where I think some of the biggest gains can be made from applying category theory to this sort of modeling discipline. So here, for example, is a more realistic sized causal loop diagram. It's from a paper trying to describe some of the issues involved in COVID, and you'll may have trouble seeing all the details of it, which is part of the point. COVID is what people now call a wicked problem, meaning that it's many interacting problems, interacting in a very complex way that's difficult to get a grip on. So here you'll see this green stuff as various economic aspects of COVID. The environmental aspects are here. I guess governmental aspects or interventions in general are here. There's, of course, the health side here, and then there's a very large issue of social dynamics here. You'll see, although maybe it's almost invisible, that there are all these edges labeled with pluses and minuses, and so it is an example of a causal loop diagram. We could zoom in on it a little bit and see some of the social aspects here. And so being able to work with these large models is important in trying to deal with complex problems, and we need to be able to deal with them compositionally. We need to be able to study these models a bit at a time and then stick them together. From System Archetype Basics, this book I mentioned, we get lots of examples of much smaller causal loop diagrams, which you may find sitting inside the larger complex diagrams. And this particular one here, they call fixes that fail. So you see, it just has three entities: the symptom of the problem, a fix, but then a fix may have an unintended consequence. So the idea is that the worse the symptom gets, the more you try to fix it, and the fix does fix it, so it tends to reduce the problem symptom, but the fix may have a delayed unintended consequence, and then the unintended consequence may increase the problem symptom. So this is a very typical sort of issue in everything. And you'll notice that it's a causal loop diagram. It's a graph with edges labeled by pluses and minuses, but there's an extra feature here that I'll have to get back to you later about this extra kind of way you can label an edge with a delay. So here's an example. Well, let's see, here's an example of that archetype. So if you need cash, you can solve that problem in the short term by borrowing. That will reduce your need for cash. But then there's a delayed effect, which is you have to pay payments with interest, and that may increase your need for cash. So probably half the people in the world, at least, probably I should say like 80% of the people in the world, their life is sort of heavily influenced by this particular system archetype. So it's fascinating to me that things that really matter to people in the real world can be seen as instances of a purely mathematical structure that's as simple as a signed graph, or maybe a graph where some of the edges also have delays in it. So as a mathematician, of course, that really fascinates me because we like simple things. So what's going on here? Well, one thing that's going on here is that if we forget about the delay for a minute and just think about plus and minus, it's really crucial that we started multiplying pluses and minuses when we're trying to figure out things like the effect of feedback loops, right? So here, if you You multiply this plus and this minus, you get minus, and so that's what we call a negative feedback loop, and so on. So there's a little multiplication table of plus and minus that we all learn, although people seem to quit math when they are told that minus times minus is equal to plus. For many people, that's going too far. So you just have to tell people, well, minus is like turning around. You turn around twice, you're back where you started from. If they'd only been taught that, maybe it wouldn't seem so weird. But anyway, mathematicians call this little monoid the abelian group Z mod 2, but here I'm thinking of it in a more multiplicative way, so I'm writing it as plus and minus. And so these are the basic edge labels in system dynamics. They sometimes call the elements of this, or maybe other monoids, polarities. Polarities indicating the idea of polar opposites, plus and minus. So that's where the term polarities comes from in my talk. But look, there are other monoids that are more complicated and interesting that you could use to label edges. For example, if you want to incorporate delays, as we often need to do, you could use that two-element monoid times some other monoid. Here's the Boolean monoid, f false and true, where the monoid operation is and, so true and true is true. And that you could use if you just simply wanted to record whether or not there is a delay on the edge. So that it could be, if the edge is labeled with false, there's no delay. If the edge is labeled true, there is a delay. And then if you have a delay followed by another delay, that's true and true is true. So that, yes, there's still a delay. Or you might want to take a more quantitative approach to delay and talk about the amount of time in the delay. If you're trying to keep things very simple, you could just let the amount of time be measured by a natural number and use addition of natural numbers in your monoid to keep track of delay. So like a 3-second delay followed by a 2-second delay is a 5-second delay. So you could keep track of both delay and this positive or negative effect in this slightly more sophisticated monoid. But as we began to study the system dynamics literature, Aditya and I, we noticed a lot of other interesting monoids that get used. So mathematically, one way to get a new monoid from an old one is to throw in a new element, which you could call 0, which is absorbing. So an absorbing element is an element which, when you multiply it by any other element in your monoid, gives this particular element. And so you can always find a larger monoid containing a given monoid with an extra absorbing element. And if you do that to the monoid plus minus, you get a 3-element monoid, which you could call plus minus and 0, and it has this multiplication table. So the old multiplication is sitting inside this larger one. 0 times anything is 0. So what's that good for? Well, you can use it for different things. You can use 0 to mean an effect of unknown sign. So like a positive effect followed by I don't know is I don't know. Or it could be used to indicate an effect whose sign depends on the circumstances. You might also use it to mean no effect at all, but it's easier just to use the absence of an edge to indicate no effect at all in one of these graphs. So this is a very nice monoid. Mathematicians will call this monoid the multiplicative monoid of the ring integers mod 3. The integers mod 3 has 3 elements, which you could call 1, minus 1, and 0. And when you multiply them, it works according to this method. But you can do other things. For example, you can take any monoid and you can create a larger monoid by throwing in a new identity element. Your monoid always has an identity element. A monoid is has an associative operation and an identity. So if you throw in a new identity element, it displaces the old identity. That's not the identity anymore, because when you multiply the new identity with the previously existing identity, you get the previously existing identity. So this new identity follows this identity law. So if you do that procedure to the monoid I was just talking about, plus minus 0, you get a 4-element monoid with this multiplication table. So you can see from the new column and row that this new identity is acting as an identity as it should. And we discovered that this trick seems to be used in the subject of systems biology, which I will get to in a second. where you use an edge labeled by this element to mean that A is necessary for B to happen. So far we just talked about things like a plus going from A to B means that sort of the more A happens or the bigger A is, the more B is. But there could be circumstances where you want to say that A is a necessary precondition for B, which is an even stronger kind of condition. And that turns out to work well with this as this identity element in this 4-element monoid. So the idea here I'm trying to paint is that you should think of graphs with edges labeled by a variety of different monoids depending on what you're trying to express. So what was this business about systems biology? Well, there's a sociologically quite distinct community to systems dynamics, as far as I can tell, which is using very similar math, called systems biology. And they use diagrams that are sometimes called regulatory networks or sometimes called disease pathways if it's applied to disease, which again describes whether certain things have a positive or negative effect on others. But in a regulatory network, these things would be different kinds of biochemicals, different kind of chemicals to be found in the cell, and the presence or absence of one of them can promote or suppress the presence of another one. And they have actually compiled very large databases of these networks. So here's part of one that you can see online, a small part of one that's for COVID. So I had drawn you a sociological causal loop diagram for COVID, but this is a biochemical version of a network for COVID, which is describing what's going on in an individual cell that's infected by COVID and how different chemicals are released, or how different genes are expressed and how they promote or inhibit other genes. So this is another opportunity to apply the math of causal loop diagrams. And we claim, after having thought about it for a while, that systems biologists do like to use this 4-element monoid I described, but of course they don't talk about monoids, and also they have their own notation. So they have arrows of different shapes for the 4 different monoid elements. So I'll call it plus is positive influence, minus is negative influence, 0 is unknown influence, and 1 is this necessary precondition, which they call necessary stimulation. It's necessary for some chemical to be present, for some other chemical to be formed. And we believe that the multiplication rules in this monoid are actually make sense if you think about the 4 elements in this way. So what's going on mathematically? Well, we're studying graphs with edges labeled by elements of some monoid. So just to be super clear, I get this picture of myself out of here. A graph is just some set we call the set of vertices, and another set we call the set of edges, together with 2 maps from the first to the second. Each edge has a source vertex and a target vertex. It's sort of amazing that there's a huge branch of mathematics. It's devoted to the study of 2 sets and 2 functions between them, but that's the way life works. And so when I have an edge whose source is V and whose target is W, I'll just write it like this. You could almost think of it as like some kind of morphism from V to W, but this is not a category. This is just a graph. So then for any monoid, you can talk about, for any monoid M, you can talk about an M-labeled graph, which is simply a graph that also has a map from its set of edges to the monoid. We'll call that map L for label. So we say that each edge is labeled with some element of the monoid. So I want to talk about the math of these things and how it connects to the applications that we've already seen in systems dynamics and systems biology. So I said that this idea of an edge going from some vertex to another should remind you of a morphism going from one object to another. And that's, of course, because a category is a graph, but with the extra feature that you can compose edges, and also that every object, every vertex has an identity morphism. So any category gives you a graph. We say it has an underlying graph where the edges are called the morphisms of the category and the vertices are called the objects of the category, and every morphism has a source and a target. But conversely, you can freely form a category from a graph. So there's a pair of adjoint functors between the category of graphs and the category of categories. There's a underlying graph of a category, but then left adjoint to that functor, you can freely form a category from a graph. So how does that work? Well, for any graph G, the objects in this free category on G will just be the vertices of G, but then the morphisms from one vertex V to another vertex W will be what we call edge paths from V to W. So they will be a sequence of edges and the source of the first one is your initial vertex V, and then you march on and on. Each edge, its source is the target of the previous one, until finally the last edge arrives at W. So this is what the morphisms have to be if you're able to compose edges, and if you do it freely, that is, if you apply no extra relationships other than those required by the definition of a category. So the concept of a path of edges, a directed path of edges, you might emphasize, because all these edges are going the same way, arises very naturally from these adjoint functors. Now, why do we care about that? Well, we'll see that we already sort of do care about it when we're talking about things like feedback loops, where you're considering not just a single edge in a graph, but a whole chain of edges, or a path of edges, starting at one vertex and ending, in that case, at itself. So we need to think about this when we're trying to think about feedback loops. Category theorists love to talk about de-looping categories, de-looping monoids, which is very confusing to those who encounter it without an explanation of what the hell it means. But this B is a mysterious symbol for de-looping. Don't ask me why, just to confuse you further, I guess, to denote de-looping with the letter B, right? That makes lots of sense. And so if you have a monoid M, you get a category with just one object called B of M, where it has one object and then it has one morphism for each element of your monoid, and you can compose those morphisms by multiplying in your monoid. So that's a very popular way to get categories from monoids, but then you can also take the underlying graph of that one object category and you get a one vertex graph. It'll be a graph with one vertex, and then it'll have one edge for each element of your monoid. So for example, if our monoid was this plus minus that I was talking about, then the underlying graph of BM will just be this little graph here with one vertex and one edge for each element of your monoid. So this is nice to think about, because then the category of M-labeled graphs is what we call a slice category, graphs over UBM. The objects in this slice category then will be graphs equipped with a map of graphs to UBM. And you'll see what that does is it maps any edge of your graph to one of the edges here, and thus labels that edge with an element of your monoid. So that's why the category of M-labeled graphs is the category of graphs equipped with a morphism to UBM. We call that construction a slice category. Similarly, we can talk about a category of M-labeled categories to be cat over BM. So what's an object in there? It's a category where each morphism is mapped to a morphism in B of M, i.e. to an element of the monoid M, in such a way that when you have two morphisms that can be composed to get a new morphism, you can multiply the labels of those two morphisms in M and get the label of the composite morphism, which is exactly what you want, when you start multiplying those pluses and minuses around a feedback loop. So this turns out to be a good structure to think about. And indeed, every M-labeled category has an underlying M-labeled graph. So this underlying functor U of M, what it does is it just takes your category, forgets the fact that you can compose morphisms and just thinks of them as edges of a graph. But it remembers the fact that the morphisms here were labeled by elements of M. That forgetful functor, it also has an adjoint functor. So there's a free M-labeled category on an M-labeled graph. And it's, again, a very natural thing that's actually implicit in what people have been doing. So what is it? So the vertices of your graph will be the objects of this category Fm of G. And the morphisms in Fm of G will just be edge paths. And each edge path will be labeled by the product of monoid elements labeling the edges in the path. So here, for example, is our little graph labeled by M, where M is the two-element monoid consisting of plus and minus. But now if we take the free M-labeled category on it, now we get a category where, for example, there will be a morphism in this category for effort to grades, and that morphism will be this edge path that's shown in blue here, and this edge path will be labeled by an element of M, and that label is just the product of the labels of these edges. So it would just be minus times plus, which is minus. And so what that is just saying is that although effort does not have a direct impact on grades, it has an indirect impact on grades because effort affects sleep, and sleep affects quality of work, and quality of work affects grades. And this particular indirect impact of effort on grades will have a minus sign, right? There's also another morphism from effort to grades, which is the one that you more likely think about at first, which is where effort has a positive effect on grades because it affects your quality of work in a positive way, and that affects grades in a positive way. But that's a different morphism. Here I'm thinking about this morphism here, which is the way in which effort has a negative effect on grades. So when you have a big complicated causal loop diagram, there are all these edge paths in it, which will all be labeled by monoid elements, which describe various indirect impacts of one entity on another. So now, as we've already begun to see in an example, there will be certain small M-labeled graphs that are important, that come up a lot. And in systems dynamics, I mentioned they are called system archetypes. But it turns out that in systems biology, they study them as well, but they think about it a somewhat different way, and they call them motifs. So far, it seems to me that the systems biologists, by the way, have been studying smaller M-labeled graphs than the systems dynamicists. I've been looking around, and so far, the systems biologists seem to be very conservative in how large a graph they want to think of as a motif. So here's an extremely small one. So here's a little M-labeled graph, which you could call the negative feedback loop. Or if you like this terminology that category theorists like, you call this the walking negative feedback loop, meaning like the Platonic archetype of a negative feedback loop. It's just a graph that has a single vertex, a single edge from it to itself, and it's labeled with a minus sign. That's like the simplest negative feedback loop. And that negative feedback loop will be hiding in larger M-labeled graphs in various ways. For example, here we see, in some sense or other, we see some kind of negative feedback loop where, for example, effort winds up having a negative effect on effort, in this case, because your grades get better and you say, I don't need to work so hard. So what I'd like to do is to understand mathematically in what sense is this motif visible in this larger M-labeled graph. In one sense, it's obvious. You can just see you go around this loop, you get a minus. But what's going on in general here? Well, it was worked out very nicely in this case where M is the two-element monoid plus minus in this nice paper with a bunch of authors who are all working together in a American Mathematical Society project in the woods, sort of near Buffalo, New York. Rebecca Adidell, James Fairbanks, Amit Kumar, Pablo Okal, Evan Patterson, and Brandon Shapiro wrote a paper, very nice paper in the journal Compositionality now, called A Compositional Account of Motifs, Mechanisms, and Dynamics in Biochemical Regulatory Networks. So they figured out the stuff that I'm about to explain, at least in the instance of this particular monoid, but it's very easy to generalize it to any old monoid. So the idea is to understand how, in what sense exactly can some simple M-labeled graph be hiding inside some more complex one, as we see in this picture here. So you see there's not a morphism of M-labeled graphs from this M-labeled graph to this M-labeled graph. That might be your first guess as to what kind of map you have from this to this, but you instantly see that it's not going to work because you would want to map this edge not to one particular edge in this graph, but to the whole loop consisting of three edges. And that's just not a map if you're talking about the category of M-labeled graphs, because an edge needs to be mapped to an edge. So we have to bring the M-labeled categories into this game. So as I mentioned, there's a pair of adjoint functors between the category of M-labeled graphs and the category of M-labeled categories. Whenever you have a pair of adjoint functors, you get a monad, which is the composite of the first doing the left adjoint and then the right adjoint. So that would be saying, take your M-labeled graph, form the free M-labeled category on it, and then take the underlying M-labeled graph of that. Whenever you have a monad, if you've been well brought up, you get interested in what are called Kleisli morphisms, the Kleisli category of that monad, and that's what's going on here. We do not have a map of M-labeled graphs from this little one to this big one, but we do have a morphism from the first one to T of the second one, where T is this monad. So in other words, this vertex here could be mapped to effort, and this edge here could be mapped to this whole loop here, which is an edge in the underlying graph of the free category on this graph here. So people in computer science like to think about the Kleisli categories of monads and use them for many different purposes, but here we see them showing up as the correct notion for seeing how a small motif can be found inside a larger M-labeled graph. So that's cute and suggests doing various tricks. So feedback loops are extremely important when you're thinking about causal loop diagrams. And so what are they actually? Well, if you have an M-labeled graph, you can form this free M-labeled category on it, and there will be some morphisms in there, which are morphisms from some object to itself, aka endomorphisms. Those will be feedback loops. So what is such a thing? Well, it will be an endomorphism in the free category on the graph, and that's just a loop of edges, or we'll call it an edge loop, but then it will be labeled by some element of M, which is the product of all the labels of the edges forming that loop. And that element of M is the feedback of the loop. For example, if M is just plus or minus, you just get two kinds of feedback, positive feedback and negative feedback. But M could be fancier, and then you get more sophisticated notions of feedback. So, for example, if we take this same darn example I keep referring to, there are, in some sense, two basic feedback loops. Certainly, there are two feedback loops. So here's one, effort having a negative effect on effort. And here's another one, this longer one. Again, has negative feedback. In what sense are they the basic ones? Well, that requires some thought. You can certainly form other loops. For example, you could form a longer loop where you first go around this and then you go around here. So there's certainly more complex loops. Also, of course, you could take any loop and you could start it at some other point. So here I said this loop is starting at effort, but you could say, well, no, I want to take the loop starting at quality of work and consider that loop. There's some sense in which both those two processes of getting new loops from old are not giving you anything fundamentally new. So in some sense, you would like to say that the loop has an existence regardless of where you start on the loop. And in some sense, you'd like to say that, yes, sure, we can build more complex loops out of smaller ones by composing them, but we would like to find the ones that aren't composites in that way, and those should be the basic feedback loops. And the idea you see in system dynamics is that you try to find basic feedback loops because those are going to be dominating the behavior of your system. And if you can address them or change them in some way, then you have the ability to control the qualitative behavior of your system. So in what sense are these the two basic feedback loops? Well, somewhat to my surprise, as I began thinking about this, it turns out that homology theory is the right answer. Well, homology theory is the study of things like loops and holes in spaces. So it's not so surprising, at least if you've studied some topology, that homology theory would be useful for taking these pictures and finding the loops in them. But one of the novel features here is that if you studied homology theory in an algebraic topology course, they would always, homology comes with a choice of what you call your coefficients. I'll explain this in a second. Some of you know about this stuff. If you don't, if you're not. But those coefficients in your typical course would always be taken to be elements of an abelian group. That's just what they do. But it turns out that here, the right kind of coefficients to use will be coefficients in a commutative monoid. So we actually need a slight generalization of the homology theory that people learn in a typical course. But it's very simple, this generalization, because we're only thinking about the homology of a graph, and a graph is a rather simple thing. So here's how it works. You can take any graph and you can turn it into a category. I already told you one way to do that. You can take the free category on it, but this is another way. You can take any graph and turn it into a category by taking formal linear combinations of objects and morphisms. And so actually that only works, I should fix this slide a little bit. That only works if you pick a commutative monoid that's an abelian group. But actually I want to be more general and let it be a commutative monoid. So here's what we do. So there's a functor called A of blank, which if you give it a set, it gives you a set X. You get this set A of X, which is the set of linear combinations of elements of X, where the coefficients, the things sitting in front of them, are elements of your commutative monoid A. This is what we call formal linear combination. If you ask mathematicians what formal means basically, don't ask me what it means. It's just symbols on the page. So we don't know a priori what we mean by taking elements of a set and multiplying them by elements of a commutative monoid and then adding them up. But we do know how to write that symbol on the page, and we do know how to add such things because we just add the coefficients using the monoid operation. We better only consider finite linear combinations, or else various nasty things will happen. So if you do this to a set, you get a commutative monoid. And so that indeed, that's a functorial process, sending any set to commutative monoid. And that's a way of sort of linearizing your problem. That is, turning your problem into one where you can now start talking about linear combinations of things. So this is a very popular operation in mathematics. So for example, if you take your commutative monoid to be the integers, then this monoid we get, A of x, actually turns out to be a group, and it's an abelian group because addition's commutative, and it's what's called the free abelian group on X. Mathematicians love that. They eat it up. But we're going to actually do a slightly different, the only reason why I mention that is I will occasionally allude to it, but what we really care about is the version where we use the natural numbers, and this then is what's called the free commutative monoid on X. So you're basically saying, give me a set X, and freely imagine that you can start adding elements of X. So you could like add y, and you get something, and you might call it 2 times y for short, and then the coefficient would be the natural number 2. And you could do like 2y plus 3z and stuff like that. And that's indeed the free commutative monoid on a set. So now what you can do then is you can take any graph and you can just hit it with this functor, and you can get something where you now have a commutative monoid of edges and a commutative monoid of vertices and source and target maps, which will be now homomorphisms of commutative monoids. I'll draw you pictures of examples in a minute, but this is a little diagram, and this is the kind of diagram that in category theory you could take the equalizer or the co-equalizer of, and the co-equalizer of this is called the zeroth homology monoid of your graph with coefficients in A. People say, as I mentioned, are very familiar with this in algebraic topology when A is actually an abelian group. And you could take the equalizer and you get something called the first homology monoid of your graph with coefficients in A. And that's what I mainly want to talk about. That's the one that I actually want to talk about because that will help us understand feedback loops. So let me explain it with some examples. Well, before I do that, I guess I just show you that, like, here's the picture. You have this, you started out with this graph. You formed formal linear combinations of edges and vertices to get this new graph where everything here is a commutative monoid or a map of commutative monoids. And then you can take the equalizer, which is called the first homology, and the co-equalizer, which is called the zeroth homology. But I only care really about the equalizer now. So let's see what it's like. So here's a graph. Here's a graph that has some, I guess, 1, 2, 3, 4, 5, 6 vertices and some number of edges. So now we're going to apply the functor n blank of g. So now what we do is we allow ourselves to take linear combinations of vertices and linear combinations of edges. So, for example, here is a particular linear combination of edges, so an element C in n of E. I've drawn the coefficients of each edge, which are mostly zeros, but there's some where the coefficient is 1 or 2. This picture here is a little bit full of cruft because these edges with a coefficient 0, we're sort of not so interested in those. So we could draw the same picture in a more lightweight manner like this, where we just keep the non-zero stuff. So this would be a way to draw an element in this set of linear combinations of edges, right? So here's this edge plus 2 times this edge. That's a picture of a linear combination of edges with natural number coefficients. So that's the kind of thing I'm talking about here. Now, remember, I'll just back up a little bit. We had the ability to take the source or the target of any linear combination of edges. So let's see what that's like. So we'll take this linear combination of edges. Now I'll take its source, and we get the stuff in blue. Namely, we get A plus 3 times E. So the idea is we look at our linear combination of edges, and we work out the sources of all of them. So the source of this edge is A, the source of this edge is E, the source of this edge is E, but notice we have 2 times this edge in our linear combination. So if you use linearity, the source of this edge plus 2 times this edge would be 3 times this vertex here. So that's the source of C. We could also work out the target of this linear combination of edges. Okay, and we get these guys in red. So the target of this edge is B, the target of this edge is A, the target of this edge is F, but we have 2 times this edge, so we get 2F, so we get A plus B plus 2F. So I hope you see the rules of the game. You start out with a graph, now you let yourself form linear combinations of edges, and you can talk about the source and target of any of those, which you compute just using linearity. Now, in that example, notice the source was different than the target. So it was not in the equalizer. Remember, the equalizer of the linearized source and target maps, that's the thing I'm really interested in. That's the first homology of our graph. You can think of this equalizer in a very simple-minded way, is it's a subset of A of E. It's the subset of A of E consisting of those linear combinations of edges whose source is equal to its target. That's why it's called an equalizer. So in this example, the source of that was not equal to the target of that, so it's not an equalizer. So here's one that, well, here's another one. Let's see about this. So here we have a whole bunch of edges with a linear combination of a whole bunch of edges. If we take the source of this linear combination of edges, we get 2A plus 2B plus 2C plus 2D plus E plus F. So you can see, for example, that this guy here is the source of both this and of this. So we get it showing up twice. Or this is the source of 2 times this, so we get it twice. So this stuff in blue is the source of this linear combination of edges. But now let's work out the target. Well, the target in this case is exactly the same. You can check that, for example, that like this guy here is the target of this edge and also of this edge. So we get this guy showing up twice. And if you go back, you can see that's just the same thing we had before. So this particular linear combination of edges called C prime here is in the equalizer. So it's an element of the first homology of our graph. So if you think about what that really means, what it means is that at every vertex, the total outflow is equal to the total inflow, if you think about it for a while, right? So the 2 coming in here, that's what makes 2dB showing up in the target, but what makes 2D show up in the source? Well, it's because it's also the source of 2 things. So it's as if electrical current or something flowing around these wires would be conserved. And indeed, there's been some very nice elementary but beautiful work relating homology theory to Kirchhoff's laws in electrical circuits. So one of Kirchhoff's laws says the total current flowing in at any point is equal to the current flowing out. So that's what homology, first homology is like. And you'll notice then that if you have any loop of edges, first that will give you you can think of it as giving you a linear combination of edges. So if I have a loop, an edge loop gamma, I can define this thing bracket of gamma to be just the sum of the edges that show up in that loop. And that will always be an element of the first homology because it's a loop. And so each vertex will have as much stuff flowing out as flowing in. So loops give you elements of first homology in this way. Now, the interesting thing about taking coefficients in the natural numbers, which is what you never learn about in school, is that the homology depends on the directions of the edges. So for example, if we have this little graph here, and you work out its first homology with coefficients in the natural numbers, well, there's one basic feedback loop, but you could create new ones by saying that loop going around twice, 3 times, 4 times, etc. And so you get one element of the first homology for each natural number. That is each natural number multiple of this basic loop. So you get n. Whereas this graph here has no loops in it, no directed edge loops. So its first homology is trivial. It's the initial commutative monoid, which is 0. Whereas when you learn about homology of graphs in school, they always start out teaching you with coefficients in the integers, and they will tell you that if you work it out here, you get z, and because you can go around this loop any integer number of times, that is, you can go backwards around this loop, and that counts as negative. And similarly, this one also gives you z, because when you use integer linear combinations of edges, you get these possible new elements of the first homology, for example, going around this one, and then plus minus plus negative of this edge. So you can go backwards along edges when your coefficients are in an abelian group. The only reason why I'm mentioning this is because that's like the usual stuff, but that's not actually what we're interested in here. We're interested in the natural numbers because we're interested in feedback loops, and this thing doesn't have a feedback loop. That graph down there has no feedback loops. So now we're finally ready to state a theorem about what are the basic feedback loops in a graph. And we can define these to be the minimal elements of the first homology. So what does that mean? Well, let's say that an element of the first homology is minimal if you can't write it as a sum of two other elements of the first homology that are both non-zero. So of course, anything is 0 plus itself, but this is saying that you can't break down that element C into smaller pieces. So for example, going around a loop twice would not be minimal because it would be the sum of going around once plus going around once. So there's a theorem that you can prove. It takes a little bit of work. It's not extremely deep, but it deserves to be called a theorem because you have to think about it a while to prove it, that any element in the first homology is a finite sum of minimal elements. So these will be our basic feedback loops. But how do you find them? What are they like? Well, actually, sorry, I'm not going to answer that question yet. Here's a little fact about them. So what does it have to do with feedback? Well, remember, if you have an M-labeled graph, that's the kind of thing where we want to be able to talk about the feedback around a feedback loop. And it turns out that if you have any M labeling of a graph, then you get a homomorphism from the first homology to that monoid. And what it does is it takes any element of the first homology, which remember is some linear combination of edges, and just maps it to the corresponding linear combination of the labels. So that tells you the feedback around the loop. Or, sorry, around a loop. So some elements of H1, remember, come from loops. Others will be linear combination loops. But by this theorem here, we will know this L tilde if we know its value on minimal elements, because everything in here is a sum of those minimal elements. So minimal elements are all you need to know the feedback around. But what are they like? How do you find them? Well, there's this nice way to find them. And it's sort of obvious if you get the picture of what's going on here. So we can say an edge loop is simple if all the vertices on that loop are distinct. So it never even crosses itself, for example, like a figure 8 kind of shaped loop would not be minimal. And then let's say the two edge loops are equivalent if the only difference between them is where you start on the loop.
You have 5 minutes remaining.
Good. Luckily, I have less than 5 minutes of stuff to say, but thanks. So the big theorem here, it's not terribly hard, but not obvious either. It's obvious until you try to prove it, that is, that there's a bijection between equivalence classes of simple loops in a graph and minimal elements in its first homology. And this equivalence just sends all the loops equivalent to some simple loop to the corresponding element of homology. So you just need to run around and find all the simple loops, the non-crossing loops in your graph. And if you know the feedback around them, you know the feedback around any loop.
Yeah, sure.
Okay. Meanwhile, I will talk. So what we're seeing here is that by pondering these rather simple-minded but very powerful ideas of examining systems in the world, whether they be social or biological, and seeking feedback loops in them, we are led to math which is the same, almost the same kind of math that algebraic topologists have been studying when studying loops in topological spaces. But the difference here is that we're interested in linear combinations of loops with natural number coefficients, not integer coefficients. So we're led to some math that's, slightly different than the math that the mathematicians had come up with. And I think there'll be a nice field of study. So what are some next things we can do? Well, certainly we want to talk about composing open M-labeled graphs, that is, graphs with some edges dangling off of the edges. For those of you who've been studying this business of structured cospans over the years, you'll know that this is the kind of thing that those people do. So there's a symmetric monoidal double category of open M-labeled graphs. So that lets you study them compositionally. A little more non-routine is the fact that you can study how this first homology monoid behaves under composition. So there we are studying what you might call the emergence of feedback loops. If you take two systems that don't have feedback loops and you stick them together, you can get feedback loops. And there's some math that helps there. There's a thing about that called the Mayer-Vietoris theorem, but we have to adapt it to this new context. Third, and somewhat more practically, you could build software to find motifs, small M-labeled graphs inside big ones. And Evan Patterson and his collaborators, as Nate mentioned, are building a software framework called CatCollab based on double categories. And they've already made some demo tools, which you can find online, for finding motifs in M-labeled graphs for some of these different choices of M that I mentioned. And that's the beginning of a lot more work, I'm sure, of interesting applications of this to real-world problems. Good, okay. While thinking about this stuff, I came up with a crazy idea, which is very speculative, but I can't resist mentioning it, which is you have these two subjects, the systems dynamics, where they talk about systems archetypes, and the systems biology, where they talk about motifs, two names for simple, small M-labeled graphs. This book, I miswrote the title, System Archetypes Basics, lists 7 of these, which are all evil. They're all archetypes that mean that when you have them in your system, it's going to cause trouble in some way or other. Interestingly, those are never discussed in the systems biology literature. Why? Maybe because people haven't looked for them, or maybe because since organisms have been evolving for millions of years, they've managed to work out some of the bugs, and that those motifs are not typically present in these what are called regulatory networks of those organisms. I want to look around on some of these databases of systems biology networks to see if those motifs are really missing, or maybe those things that cause such problems for humans are somehow also able to be used for good by organisms. And could you actually figure out what you mean by looking at a small signed graph and just looking at the graph to say, like, oh, this is a bad kind of pattern or not? That would be amazing if it were true, but it seems that there is some truth to that. So I'd like to examine this. And so that's just an example of the many type of questions you could come up with when you use the same math to view two different subjects, in this case, systems dynamics and biology, and then start colliding them against each other, and it generates new questions. Okay, thanks very much. Oh, Nathaniel Virgo. There you go. I'll read it out loud. One reason you might be interested in feedback loops is that you have a system of ordinary differential equations. You've linearized it around a fixed point, and the pluses and minuses are the signs of entries in the Jacobian matrix. Have you thought about how this stuff relates to that? Just a little bit, but that is certainly widely studied in the causal loop diagram community. So they do try to have systematical processes well, either from going from ODE and linearizing them in the way you described to get a causal loop diagram, or even to go backwards and try to generate sort of example system of ODE starting from a causal loop diagram. And so, yes, people have thought about that. And so Nate has pointed me to some papers where the word is, what are the buzzwords? Linearized feedback analysis or something like that?
Loop dominance.
Loop dominance analysis. So if you type loop dominance analysis into the all-knowing Google, you will see studies of this. But they have not brought the fancy mathematics to bear on it yet. So that is something that would be good to do. Yes.